Welcome to Season 3, Episode 11 of the 6 Lessons Podcast. Today we're going to be talking a little bit about major universities who have guided adhesive research. In the world of science, universities have always led the way, but in reality, each university is only as strong as the individuals who are in the faculty. We've talked about Charlie Cox and his great influence in advancing the science of adhesive dentistry, doing in vitro and in vivo research, and making connections with Asia, particularly Japan, the United States. In the universities, Charlie Cox had contact with University of Michigan, University of North Carolina, University of Alabama, University of California, Los Angeles. All those ideas of individuals doing research, being supported by universities, because research doesn't pay for itself. Somebody has to figure out how to make a living as they're advancing any particular science. But these individuals who are associated with universities become very important as guides to other researchers and other faculty members who would be interested in continuing the legacy of dental research. And of course, the biggest star of that type of advancement adhesive dentistry was Takao Fusuyama. And Takao Fusuyama, when he was attempting to standardize a way to decide when caries were removed from a cavity, led to the idea that the visual tactile approach was not scientific because it was not reproducible. The student that asked him the question, when should I stop my caries excavation? Fusuyama's standard answer to every student was when the dentin is hard. Most students went back and tried to figure that out. But this one particular student asked Dr. Fusuyama, how hard should it be? So the whole idea of how hard brought into question a degree of hardness that could not be communicated to the professor, to the student. And so that led Fusuyama to a quest of a scientific, reproducible technique that would allow one student to learn the same as another student, and that could be communicated beyond the visual tactile using a Explorer, which had been done for over 100 years. So caries detecting dye allowed that standardization, but it had to be developed, it had to be produced, it had to be marketed, it had to be made available. In the late 70s, it was available in Japan, didn't become available until the mid to late 90s in the United States. So the first caries detecting dye that I wanted to order had to come from Canada. And then a year later, the FDA approval for caries detecting dye came through the efforts of Ray Bertolotti's company, Danville. And other companies then had access to market that, produce that. And we had that new technology, but it was 20 years after it was available in Japan. Each bonding system has a history also. But those histories, again, usually start with the university or a particular faculty member at a university who has a question that can't be answered from traditional ideas. So Fusuyama at TMDU had to have help from an industry producer of chemicals in developing bonding systems. And the partnership that he made was with a company called Kurore. This chemical company after World War II was connected with Tokyo Medical and Dental University, and they were able to produce some organic chemicals that were polymerizable. These monomers that were developed, the first one was phenyl P, and then later on the world-changing 10-MDP molecule. This was a partnership between industry and universities. It was very productive, continues. But again, all of these relationships between individuals, universities, manufacturers who hire people to make products, there are many moving parts. It's a complex process. It doesn't just happen. Fusuyama, as he continued at his own university, had another faculty member who was not a dentist, who was a very brilliant chemist named Nakabayashi. And Nobuo Nakabayashi had his own research group outside the dental school, and he developed monomers, and he had relationships with other companies and made connections with particularly one researcher in the United States, Dave Pashley, and they wrote a book together about these ideas of hybridization of dental hard tissues. And so the hybrid layer was named by Nakabayashi. It was first described bonding a material called Severton to ivory, and then that tusk bonded to Severton was put into water and stored from 1955 till 65 and beyond. But bonding to enamel, that was the innovation of Michael Bonacore with an etching of phosphoric acid. This came in association with an institution called the Eastman Institute of Dental Research that did postgraduate training in Buffalo, New York. But Eastman, Tokyo Medical and Dental University, Medical College of Georgia, where Dave Pashley was at, started to have a network that internationally brought researchers from Ireland, for example, from England. Michael Bonacore had a good relationship with an important researcher who eventually went to Long Island, New York, the dental school. And the book that was written by Nakabayashi and Pashley was actually dedicated to this important researcher, John Gwinnett, who actually died on the eve of an important conference. And when I read this dedication to John Gwinnett, it says this, said, to all those who have participated in developing of resin tooth bonding, including our deceased friend and colleague, John Gwinnett, who with Bonacore started the bonding to enamel. And then Fusiyama, getting an idea from Bonacore and Gwinnett's early successes in the 50s, had the idea that he was going to solve a problem that related to bonding to a product called the smear layer. And so the smear layer was produced with the preparation of dentin. It's just chopped up dentin. And the first bonding systems were bonding to this smear layer. And the bond strengths were very low, 4 megapascals. And it was identified as a problem. And so the removal of the smear layer, Fusiyama's innovation was to remove it. He called it conditioning. They would condition the dentin by removing the smear layer with this same process that Bonacore and Gwinnett used in making the micro etching patterns on enamel that were able to interact with the adhesive monomers. And so the hybrid layer enamel, it was established, but it's a pretty simple connection with one material, hydroxyapatite, and one adhesive material. But then the dentin was a much more complex hard tissue because it not only had this inorganic hydroxyapatite, but it had organic collagen and 20% water. So it was a flexible, gooey, encrusted with a more hard hydroxyapatite connection, and it's very different than enamel. But the idea of using this phosphoric acid, which Bonacore used to condition enamel, Fusiyama used it, but to remove the smear layer was the first goal. But it also removed hydroxyapatite to a level of about 5 microns in the dentin. And so these bonding systems now had to negotiate this denuded collagen that was now moisturized from the pulp, which had been tubules opened up by removing the peritubular dentin. And all of a sudden, you've got moisture that has to be dealt with in the reactions. First bonding system that Fusiyama had got bond strengths about double of what the bond strengths when they were trying to bond to smear layer. They got into 10, 11 megapascals, which actually was something that was very significant. Fusiyama could see that this was actually bonding to this flat surface of dentin. That's the first beginning of a bonding system. And when that was introduced, there were other bonding systems that tried to use a similar approach of acid etch, but they had proprietary restrictions on the monomers that they could use, because once you make your own organic monomer that's polymerizable, you have the ability to legally protect that for 15 to 17 years through a patent. You've done the research, you've done the time, you've invested money. Now the laws of most lands allow you to make back your research and development costs and then make a profit, and you're protected by a patent for this period of time. And so other companies around the world started to make their own monomers and tested them in conditions that were similar to the tests, flat surfaces, and the conditioning of that smear layer with acids. Many different types of acids were tried. All of these have a history that go from the late 70s, 80s, and into the 90s. During the 80s, the company Couare had a head start and were making progress, but other companies hired other chemists and developed other systems, and they were competing on the market and sold to dentists. So this University of TMDU with this university in Georgia with called the Medical College of Georgia with Dave Pashley. Fusiyama at TMDU had 2 graduate students that were granted PhDs under Fusiyama. And the first student was Dr. Inokoshi. Second student was Dr. Tagami. And, 4 years of intense research with what had been and what is being developed put this university at the forefront of developing what would be called a gold standard bonding system. But soon other chemists associated with other companies, most notably Kerr Company out of Michigan, hired a young chemist named Al Kobashigawa. And Al Kobashigawa, a friend of mine from Los Angeles, went to Cal State Los Angeles, got a master's in chemistry, and developed a recipe for a bonding system that is still to this day very productive. And the monomer was called GPDM. And that GPDM came from a search of the literature of bonding systems that had been patented in the past. And the first one was in 1951, and that was that Severtron bonding system that was used by Bonacor when he first bonded to enamel, 1955. So 1951, a patent for this monomer that polymerized, which is a derivative of a monomer similar to Caston's epoxy monomer, was used by Severtron. But Severtron had a huge problem. Once it had the adhesive bond to the hard tissue, the bond was stretched and broken almost immediately because the actual restorative system, which was polymethyl methacrylate, shrank so much that the bond was stretched by the connection of the bonding system to the shrinking material that was trying to bond to the hard tissue, but it was pulled away, and the bond only worked on a flat surface. And hardly any cavities in 1950s were on flat surfaces. But these are all part of the historical development because Al Kobashigawa in Los Angeles was able to say, okay, this monomer polymerizes. Maybe there are other things that we can do to modify this. And one thing they did in the bonding system, they add a filler because a filler will decrease the shrinkage of a polymerizing polymer. And so they created a filled adhesive, and that filled adhesive is Optibond FL. The FL stands for filled, and that was a patented development that Kerr benefited from greatly in the past and still can benefit if you use the Optibond FL and not one of the more simplified bonding systems that also carry the name Optibond. And so as we see how science and universities and manufacturers all are independent, but they need to work together. This university that was first connected to Japan through Nakabashi and Pashley's relationship, which was called Medical College of Georgia, became a real center for researchers from Asia and also from Europe. University of Geneva brought in a researcher to Medical College of Georgia named Bernard Cucci. I may not be pronouncing his last name correctly, but he went there. But most of the researchers that came to Augusta, Georgia, to the Medical College of Georgia to work with Dave Pashley were connections with Tokyo Medical and Dental University. And those researchers who came to Georgia for a year usually came back with new innovations, new ideas. Probably the biggest one was the microtensile bond test that Hidehiko Sano developed. I believe it was first inspired to a degree from Nakabashi. I've had a conversation about that with Sano. I can't remember the exact details, but the microtensile bond test became the gold standard for testing these hybrid layers' strength. The original shear tests that were used that were very amenable to using an Instron machine, they were easy, they were fast, but the problem is they had a concentration of stresses that were shearing that actually concentrated stresses in the dentin instead of at the hybrid layer. There's details on that maybe we'll have another lecture about, but only the researchers who actually do the research or develop the protocols have the real depth of knowledge to say where are the weaknesses of my system of testing or my system that's being tested and where are the strengths. And so developing this idea of analysis, it's a very small community, and that community has to be continued so that science isn't lost. Probably the best example of almost losing important science was also in this period of the 1980s when the research on caries detecting dye and early bonding systems out of Tokyo Medical and Dental. There's a university that is in Europe that's also being supported to test these new bonding systems. And that university was in Amsterdam. Dutch acronym is ACTA, A-C-T-A. And in 1984, 1987, a major researcher named Carol Davidson, who had a physics degree, had a doctor's degree, but not in dentistry, but in physics and in engineering, he was able to develop mechanical systems to test bond strengths and to test shrinkage and shrinkage stresses. And these systems of bonding and systems of restoration, these composites which were the combination of the polymerizable molecules by having a more filled composite material. These were being developed in the 84, 87 timeframe. One company, 3M, was very progressive in that time period. They'd been working on dental composites since 1965, actually, basically using a polymerizable resin matrix called Beast GMA, developed by Raphael Bowen, called Bowen's resin. Bowen's resin was first used as a filled adhesive in 1965, given to a friend of mine, Paul Belvedere, in Medina, Minnesota. Paul Belvedere was the first dentist to put a tooth-colored material that didn't shrink too much, like the original polymethyl methacrylate did. That was the beginning of the 3M composites, which to this day have a very prominent place in restorative dentistry. But again, a company like 3M, they at some point have to get these materials into practicing dentists' hands. Paul Belvedere was the one who started and had a teaching career for his whole career. The Academy of Biomedical Dentistry in 2014 gave him a special Lifetime Achievement Award in Los Angeles. Dr. Belvedere and his wife, good friends, were very closely associated with an early member of the Academy, Mark Maltrud, still practicing in Minnesota. The combinations of universities, manufacturers, scientists, and practicing dentists, it has always been a very irregular development and partnership. But all of those are important, because eventually, if a tooth is going to be filled, it's going to be filled by a practicing dentist. But the practicing dentist can't develop the science and manufacture the product and teach the ideal technique. All of these things should be happening in a dental school to the dental students before they graduate, but it's been a slow, agonizingly slow process in my view. It should have happened much faster, but each dental school went on their own timetable based on faculty members who may have or have not been up to date on products and particularly techniques of how to use the products ideally. So let's see, we've talked about Tokyo Medical and Dental, other dental schools in Japan, particularly Okayama University, Tsurumi University, Osaka University. All of those universities were working together at some level and started to produce graduate students, particularly in Osaka and Okayama University. The PhD graduates there have done important research over the years. In Europe, Amsterdam influenced other schools. But again, this idea of polymerization stresses was not developed fully or continued to be understood in a way that can have practical clinical success. C factor was developed at Amsterdam. The ratio of bonded to unbonded surfaces makes a prediction about the stresses of polymerization to the composite and the hybrid layer. But the C factor has to be relatively understood in where it is being bonded to the material. And that difference of the configuration of the cavity, so C stands for cavity shape or configuration of the cavity, I had to figure out that there was a difference of hydroxyapatite in each bondable surface. Each dental hard tissue, which would be enamel, obviously, dentin, but dentin needs to be understood at 3 levels: superficial dentin, intermediate dentin, and deep dentin. All 3 of those dentin layers have different percentage of hydroxyapatite. The more hydroxyapatite you have in a surface, the faster the rate of polymerization. The deeper you go into the dentin, the more slippery and the more flexible. You have more collagen and more water the closer you are to the pulp. It's very different than the area that's close to the DEJ in the enamel. And so if there is a competition of these different areas, meaning they are connected to each other, these different layers of what we have named the hierarchy of bondability are connected to each other too soon, then the flow of the movement of shrinkage, the actual dynamic or the polymerization dynamic, the direction of shrinkage will be towards the more mineralized surface. In other words, if you connect dentin to enamel too soon, the shrinkage moves towards enamel. But even in the dentin, if you have deep dentin connected to superficial too soon, then the stretching and the weakening of the hybrid layer next to the pulp is compromised, and it moves towards the DEJ. You don't want that if you're trying to protect the pulp from potential future infection through a compromised or a debonded hybrid layer. The understanding of the C factor was very influential in my early investigations, but I soon understood that you had to understand these levels of mineralization, and you also had to understand, are you using a chemical cure or a light cure material? Because these have very different rates of cross-linkage, which increases what's called the modulus of elasticity, which increases the stress. And almost no chemical cure materials are used now in restorative processes. But the chemical cures that were first tested gave the numbers and the conclusions that had to be reinterpreted into these new fast curing, which actually had a higher degree of polymerization of the monomers. So that had a better durability in a functional situation. All of these confounding variables had to be understood and managed to have an optimal bond strength and an optimal wear situation of the restorative material. The integration of the numbers coming out of Amsterdam and the numbers coming out of Tokyo, numbers coming out of Georgia, all of those had to be evaluated. And the university that gave us the most number evaluation, the best statistical analysis of all the in vitro and in vivo data that was being produced 70s, 80s, 90s, into the 2000s, was in Belgium. And that was at a university called the Catholic University of Leuven, Belgium. And that university produced a PhD student in 1993, Bart van Meerbeek, who is still active today in 2025. Next month, Davey and I will be lecturing on an international stage with him again. We've been together in Turkey, been together in Brazil, Chile. Van Meerbeek has evaluated more in vitro and in vivo tests than any other researcher. He has 7 or 8 PhDs that are working on his team, but he also is training postdoctoral and doctoral students there from around the world. In my view, there's been 4 major universities that have put together the most pieces of this puzzle. TMDU in Tokyo, ACTA in Amsterdam, Medical College of Georgia, and Catholic University of Leuven, Belgium, still under the direction of Bart van Meerbeek. But many other universities have taken advantage of the leadership of those 4 schools and produced PhD faculty members. But then the faculty that gets trained, how do we get that information into the curriculum so that students coming out of Japan or students coming out of Holland or students coming out of the United States or out of Belgium, that transfer there has a bottleneck. And there are hundreds, if not thousands, of dental schools around the world. We estimate that there are 2 million dentists that are doing something to a tooth every day around the world. How many are using very old materials like amalgam, very old techniques like crowns, causing pulp deaths, which traditionally has been a problem of any type of mechanical retained fillings or crowns? All these dentists around the world, I would say all of them have some idea of adhesive dentistry. As we're trying to figure these things out, we do have a fundamental knowledge base that comes from these 4 universities. In the 130 articles that we train in our system that we call the 6 lessons approach, most of the articles that we are studying and using to form our protocols, what we do on an everyday basis, have some connection with those 4 universities, either in the development of materials and techniques, or the production of materials, or the teaching of techniques, or the evaluation of how these materials and techniques relate to each other. One study that nobody has talked about called Shono, and Shono showed that the biggest variable in any operative procedure is the actual dentist that is doing the procedure. In other words, you can have materials, a dentist can do different things with the materials, but the different techniques are variable upon how that particular dentist is doing the techniques, which is a direct relation to his education and how he's been educated and tested. But of course, then the dentist has to remember what he was educated and tested on, and the dentist has to do it. I mean, all these confounding variables eventually come to the heart and soul of what the dentist has as far as integrity and desires. If a dentist doesn't care about a tooth, he doesn't care. If the patient doesn't care about what's happening to their tooth, any dentist will do. But the outcomes can be hugely different between immediate failure and long-term success. I believe with all my heart and soul that science is the way forward in dentistry. But the art of how the science is applied does have some variabilities. And there are 2 or 3 ways to do maybe many of the things. For example, the gold bonding systems that we talk about, we've identified 4 that are very obviously head and shoulders above the other 60 or 70 bonding systems you can buy around the world. But the other bonding systems benefit from the chemistry, which is patented and revealed in patent applications. And as soon as a patent expires, there's a good chance that improvements by using the material that was patented are now implemented into the new bonding system. But the method of teaching and the method of applying the science is still given the fruit of long-term success since we've been using them since 1998. 1998 was the first bringing together of the 6 lessons in my office, and I practiced those 6 lessons from 1998 until 2003. And after that 5 years of what I would call beta testing in my own office, I had the documented cases that I had seen: elimination of sensitivity, elimination of retreatment, elimination of pulp deaths, elimination of full coverage crowns, all of these things for 5 years. And as I talked to my friends and said, would you be interested in learning a technique of dentistry that can prevent endo and prevent crowns and have higher patient satisfaction because sensitivity is eliminated and pulp deaths is eliminated? As I made those offerings to dentists, first locally and then in our state and then nationally, obviously, that's what the foundation of the graduate network that we have in the 6 lessons. And we would invite each of you to investigate and hopefully join with this group that's been doing successfully these advanced adhesive procedures for well over 20 years. Until next time, get bonded, stay bonded.